All right, well, welcome everyone to our astrobiology seminar. Thank you for coming. Just a quick announcement before we get started today. The speaker for next week is going to be Shuai Li from SOAST. We'll be talking about evidence for exposed water ice on the moon. All right, so today we have two people speaking. We're going to have Dan Huber and Ashley Chontos, both from IFA. They're going to be speaking to us about exoplanets and their host stars searching for habitable worlds. Dan is a recent new faculty member at IFA, and Ashley is a starting third-year student. And they've both been working on exoplanets and astroseismology, so we'll hear all about this exciting field today in their joint seminar. And just since you guys are a little bit new to this process, very typically our audience likes to interrupt and ask questions for clarification, tends to be fairly interactive, so if you would prefer it not be.
No, please do, absolutely. No, interrupt at any time. That's perfectly fine with me, as long as we stick to time, I guess. We'll try. Okay, thanks, Karen. So I will be talking about exoplanets. It's, as many of you will probably know, a very exciting field, especially in the last decade or so. We've learned a lot about planets outside of our solar system. The way that we have structured this is that I will start with giving sort of a low to mid-level overview of exoplanet science. I'll focus a little bit about, first of all, how do we actually detect exoplanets? What have we learned in the past? A little bit of a focus into the habitable zone exoplanets, those that are most important or most interesting for astrobiology. And Ashley will then take over and talk about one specific case study where we have used the tools of astroseismology and everything that we have available to characterize one particularly special exoplanet system. Okay, so why is exoplanet science so exciting? This is an animation that I will play in a second that shows you the mass of planets on the y-axis versus their period. And the dots that are on the plot right now are the planets that we know that we have in our solar system. And this is the case of how things stood in 1990. And as I start this animation, you will see planets populating this diagram. So obviously before 1995, we only knew of the solar system planets, and then we started to discover lots of planets, especially up here, these large, massive planets, Jupiter mass and larger. At some point, Pluto here will disappear, as you will see. No, it's actually taking into account, there it goes. And we fill up this diagram more and more over the years, more and more exoplanets have been discovered. And you can also notice that the first planets were the most massive ones, but then we start to fill up this bottom part of this diagram quite rapidly. That is mostly due to discoveries by the Kepler mission, which I'll talk about in a second. So this was just essentially 2 decades, and we have gone from not knowing about any planets outside of the solar system to now knowing thousands of them. And and the main goal of exoplanet science over these past 2 decades has really been to try to understand this population of planets. Where do they come from? How have they formed? What are their properties? Are they rocky? Are they gaseous? Are any of them like Earth? So how do we actually detect planets? I'll walk you through the sort of main detection methods. Many of you will probably know this. If it's too slow, let me know, and I'll move a bit faster, but perhaps for the students, a bit of an introduction into detection methods. Observationally, how do we actually find them? The first method makes use of the so-called Doppler effect. So if you have a planet that's orbiting a star, both of them will in fact orbit a common center of mass, and the star will move backwards and forwards. And if we look at the system and we actually monitor the redshift and the blue shift of the light, for example, for spectroscopy, as the star wobbles back and forth because of the gravitational influence of the planet, we can discover the planet around the star. So this is, the Doppler method is the very first method, in fact, to be employed to find exoplanets, and it has yielded, what is now commonly accepted to be the first detected planet outside our solar system, the 51 Pegasi. So here's a graph which shows these velocity measurements. So what you actually measure in the spectrum is the velocity, redshifted and blue shifted. And if you fold it against the orbital period of the planet, as shown here, you get this nice sinusoidal signal with the amplitude k, so the amount of velocity that you measure from the star being essentially proportional to the mass of the planet. So here's the expression down here for k. So the more massive the planet, the larger the signal, the velocity signal will be, the Doppler shift will be that you have to measure. So the Doppler method is sensitive to measuring the planet mass, of course the period, and also the eccentricity, so the shape of this curve will vary depending on whether the planet is in a circular orbit or an elliptical orbit. It's mostly been applied to solar-type stars. The stars are quite similar to our sun, but it's also been extended to other stars. And what it requires is high-resolution spectroscopy. So you need an instrument that essentially splits up the light into different wavelengths, and you measure the wavelength shift. Currently, so keeping in mind that on the astrobiology aspect, the second Earth, finding an Earth around the sun requires you to measure the velocity to a precision of 10 centimeters per second. So it's a very, very small shift that you have to measure and that you have to disentangle away from all the other effects that affect the measurement. Currently, we're at about a meter per second precision. So currently, we're still not able to detect an Earth analog using the Doppler technique, although that's already being worked on and will be improved in the future. But currently, we cannot do this. Second method is the transit method. That's in fact the method that we'll be mostly talking about, and that is the one that's employed by Kepler to detect exoplanets. That's very similar to the Doppler method, quite straightforward. You observe a star, and if the geometry is right and the planet crosses in front of the stellar disk as you observe the star, and as you just measure the brightness as a function of time, what you will observe is a dip in your light curve because of the light that is being blocked. So you measure the brightness as a function of time. As the planet moves in front, you get this dip. This dip will repeat itself every orbital period, and hence you can measure, you can take an exoplanet and you can measure its orbital period. The other thing that transits tell you is the size of the planet. So the size of the dip that you measure, this delta factor here, depends on the ratio of the size of the planet divided by the size of the star squared, because it's essentially the areas, it depends on the area that is being blocked. So if you know the size of your star, and that's one of the key points that we're going to convey to you today, that that's actually important and not as easy to do. If you can measure the size of the star and you measure the size of your transit depth, then you can get the size of the planet. So transits give you the radius of the planet and the orbital period. It requires long photometry, so it's simply just measuring the brightness of stars. And the good news about the transit method is that we're actually capable of detecting an Earth already. So the photometric precision from space, for example, using Kepler, is about 10 parts per million. And the signal that the Earth causes crossing in front of the sun is about 80 parts per million. So we are capable with current technology to find an Earth analog around a star like our sun. All right, the third method that I'll briefly touch on is direct imaging. And I mentioned this one not because it's been very successful so far, it's been somewhat successful, but because this is really the method of the future of detecting and characterizing exoplanets and looking for life. As the name says, direct imaging simply consists of the fact that you have a star, the star is very bright, you can't see the planet, so you do some clever tricks to essentially mask out the light of the star, either through a coronagraph or through adaptive optics or other optical techniques. And as you block out the light of the star, you can see the light of the planet, the reflected light of the planet. And you can measure that, and first of all, to detect the planet, and second of all, to characterize it. All the other methods were indirect, right? We only measure indirectly what the planet does to the star. So direct imaging is very, very powerful because by the fact that you can actually measure light from the planet. You can measure its luminosity, you can measure its orbit, its inclination. You can also say something about its atmosphere. If you measure that light in different wavelengths, you can essentially get a spectrum of the planet itself. But it's difficult. It requires very precise, very high resolution measurements, usually done using adaptive optics. And the signal itself, how bright the planet is, that depends on the age of the planet. So if you imagine you have a very large planet, Jupiter, that's being formed, as it forms, it's very hot and very large and gives up a lot of radiation. So it's easy to see, but as they cool down, they essentially cool down and they become less bright and hard to detect. For our sort of astrobiology check, can we detect an Earth analog using this method? We're still way off. So if you look at these numbers down here, current best contrast that we could reach is 10 to the minus 6, 10 to the minus 7, so about 1 million contrasts from the star to the planet. Jupiter is about 10 to the minus 9 contrast, and the Earth is 10 to the minus 10. So we're still something like 3 orders of magnitude away from reaching the required contrast to block out the star light and detect an Earth around another star. So that might sound a little bit depressing, but of course that's one of the, I think, things that are in the technology and in instrument development, a lot of time and money is being invested to change that. In the meantime, I thought I'd show this. This is actually one of the most famous direct image systems, HR8799, also shown here. We've now been monitoring the system for so long that we can actually make a movie of planets orbiting another star. So this is real data. This is not, an animation or an artist's conception. But this is HR8799 in the middle, blocked out, so you can't see the light. And these are 4 planets that are orbiting it over a time span of something like 6 years. You see the counter on the bottom left. So we can now actually measure planets orbiting other stars. But keep in mind that these are very large planets, massive Jupiters at very large distances. So these are nothing like what you might expect to see in the solar system. But hopefully we'll get there in the future. Okay, just a note that in terms of adaptive optics, we're here in Hawaii, of course, on the sort of front line of this technology. We have many facilities, large telescopes that all use adaptive optics imaging to improve the image quality. Essentially what you have to fight against is the atmosphere, which perturbs the light as you detect it in your telescope. And a lot of them are using laser guide stars to correct for this. And in fact, the image, this movie that you've seen just before, this movie right here, was made using observations from the Keck telescopes. It's shown up here on the top right, on top of Mauna Kea. So Hawaii is really sort of leading the way in adaptive optics imaging in the Northern Hemisphere towards detection of exoplanets. Okay, so this is sort of an overview into exoplanet detection methods. One that I haven't mentioned is microlensing. It's also still a sort of niche detection method. But one thing that I want to just pause a little bit and ask you, what do you think, in terms of these 4 methods, which one has detected the most planets that we know of so far? So remember this first movie that I showed you, all these thousands of exoplanets. Which one do you think has detected the most planets, and which one has detected the least amount of planets? Or if you feel very confident, maybe you could put some numbers on these percentages that I put up here. Anyone? What's the most successful method?
Well, I feel like the transit method is going to be the most successful because that's what Kepler primarily did. Kepler's kind of
correct.
Amazing.
Correct. Do you want to put a number on it, an estimate of what percentage of exoplanets get tested?
Maybe like 80% or that high.
80%. Clearly, I'm a winner. 80%.
Get a free cookie.
Should have some prizes to give it. 80% of all exoplanets have been detected using the transit method. 18% have been detected using Doppler velocities, and the rest using direct imaging or microlensing. So that means that 98%, in fact 99% of all exoplanets that we know today have been detected indirectly. By indirectly, I mean that we're measuring something about the star, and we're measuring the influence of the planet on the star, right? Here we measure the amount of light that we lose because the planet goes in front of the star. Here we measure the blue shift and the red shift of the light because the planet pulls on the star. And the same thing happens in microlensing, although it's a little bit more complicated. Direct imaging is the only way we can directly actually measure something about the planet. And this is why characterizing the star is so important. So this is why stellar astrophysics has such a strong analogy, a strong importance for exoplanet science. And there are a whole slew of methods to characterize stars, so measure their masses, measure their radii, measure their temperatures. You might think, or you might have heard, that characterizing stars is easy or a solved problem. It's not the case. To convince you of that, I could give a whole lot of talk about all these sort of methods of what we do. You can, for example, measure the parallax, so the distance to a star. That gives you an idea about its size. You can measure photometry, so it's light in different bands. You can do spectroscopy, so you can essentially just split up the light into different wavelengths, measure the absorption lines, and learn about the star this way. Or you can also do astroseismology, which is a pretty new method that, in an elegant way, actually uses the same data that we use to detect transiting planets, and with just photometry, to learn something about the stars. So astroseismology is the measurement of stellar oscillations. So you see these oscillations in the light curve, so that the intensity goes up and down because of pulsations within the star. We use those pulsations to learn something about the properties of the star. I won't go into a whole lot more detail because we're talking about astrobiology. Ashley will talk a little bit about it, characterizing the system she will talk about. But just keep in mind that that's a very good method to characterize the stars.
What does astroseismology tell you about planets?
It tells you something about planets in an indirect way by characterizing the star. So if you measure a transit, right, you measure this delta factor, which is RP of our star. So you need our star to learn something about RP, to measure the planet radius. And the radius of a star is not a trivial thing to measure. But astroseismology gives you a handle on this because in the simplest way, think about the frequency of a wave propagating through some cavity depends on the size of the cavity it's propagating through. It also depends on actually the composition of the gas that's within the cavity, but to zeroth order, it depends on the size of the cavity. So a star is oscillating with a lower frequency the larger it is, and it oscillates faster the smaller it is. And this is in fact what we see in stars. This is a time series of the sun. If I would show you the same time series over 4 hours of a red giant star or an involved star, the period of the oscillations would be much slower. So by simply measuring how quickly a star is oscillating, we can get a very good handle on our star, the size of the star. And that in turn gives it a radius. But directly of the planet doesn't give you information because the signal comes from the star. Okay, I have to make sure that I'm not eating into my time. So let's talk a little bit about exoplanet demographics. So what have we learned about planets over the last decade or so? And what I will be mostly talking about are results from the Kepler mission. We've mentioned this already a couple of times, but just to recap, Kepler is still a NASA space telescope that was launched in 2009. And you can see Kepler here before launch. It's a large photometer. Essentially, it's a 1 meter telescope. And the whole point of Kepler was to just measure the brightness of stars as precisely as possible and for as long as possible. So Kepler looked at one patch of the sky, just above the galactic plane here. So this is the field of view from Kepler. It looked just at this patch of the sky for 4 years and measured the brightness of 150,000 stars continuously. That's all it was built for. It's a very simple experiment to find transiting planets. As I've said before, it was built to find transiting planets, but coincidentally, the data was also very, very well suited to do astroseismology because we used the same data to do that. So, which stars did Kepler observe? This is an HR diagram, a modified HR diagram showing the radius of the star on the y-axis versus its temperature. Our sun, as a reminder, sits around here, so about 5,800 Kelvin and 1 solar radius. And you can see this is a number density plot, so red is a large number of stars. These are all the stars Kepler has observed. Most of the stars that Kepler has observed are solar-type stars, G-type stars, sit around here. It also observed a few cool stars, so cool dwarfs, K and M-type dwarfs that are much smaller and much cooler than the sun, and also a sizable fraction of red giants. Most of these were actually observed for astroseismology, not to find planets. So Kepler really focused on the solar-type stars, the ones that are circled here, and it has revolutionized our understanding of exoplanets. And I'll show you this in these two graphs. This one shows planet masses over the periods, the same thing I've shown before in the animation, but now showing all the exoplanet discoveries prior to Kepler. And in the plot, the masses of Jupiter, Neptune, and Earth are highlighted. So these are sort of the solar system comparison points that we can look at. So this was before Kepler. Before Kepler, 85% of all planet discoveries were larger than Neptune. So everything was larger than Neptune. Most of them were, in fact, Jupiter mass planets. And this is how the picture looked like after Kepler. After Kepler, 85%, or with Kepler, 85% of all discoveries were in fact planets that were smaller than Neptune. See in yellow here, overplotted these discoveries from Kepler. Kepler, of course, measures planet radius. You need to do some conversion between mass and radius. But most of them were, in fact, between the size of Earth and Neptune. And some of them, in fact, were even smaller than the Earth. And that is because of the fact that what I've mentioned before is that we can actually do photometry from space quite precisely. And we can push down towards the detectability of Earths. So I'm skipping a lot of steps here, but the sort of main message, one of the main lessons that we've learned from Kepler can really be summarized in this plot. And that is that you can turn these detections that you see here into an occurrence rate. You can say, okay, this is my detected sample of planets, but how frequent, if I look at any other star other than the Kepler field, how likely is it that I will see a given planet around that star? What is the occurrence rates of planets in our galaxy? And this is sort of summarized in this plot, which shows the occurrence rates of planets, the number of planets per star in a given orbital period bin, so 85 days or less, as a function of the radius of the planet. So it shows you how frequent, how often planets of a given size occur. Yeah. Sure.
Which of the rocky planets do you not know?
I'll get to that. So what the composition is, yeah, I'll get to that in a second. So right now we only talk about radius. So that's all. That's the only dimension we're talking about so far. So there are a couple of lessons that we learned from this. The first one is that close-in Jupiters, so-called hot Jupiters, one of the concepts that Ashley will talk about, are actually quite rare. Those are the first ones we found. The very first planet we detected, 51 Peg, was a hot Jupiter. But if you look at them in an ensemble population study, they're actually quite rare. And then the second key result is that these, what we call now sub-Neptune-sized planets, or here they're also called super-Earths, so anything between Earth and Neptune, are actually very common. So those are some of the most common planets that we know, or that at least we have in the direction of the Kepler field, are those planets between the size of the Earth and Neptune. Now, why is this important, or why is this a curious fact? Well, it is because there is no analog in our solar system for any of those planets. The most frequent planet that we have discovered outside of the solar system does not exist in our solar system, except maybe if Planet 9 exists. Some of you might have heard that there have been predictions that there's a planet very far out in the solar system, and some of those predictions that has been indirectly predicted, and some of the estimates, some of you can correct me if I'm wrong, actually place the mass of this Planet 9 in the regime of being sort of a sub-Earth or sub-Neptune.
What does the term ice giants?
Is it on here?
No.
So ice, well, I mean, an ice giant, it depends on the composition, right? I mean, an ice giant would be something larger than Neptune and smaller than Jupiter, depending on what the actual composition of the planet would be. Whether you have a lot of, whether you think the composition is made out of water ices, things like that. In reality, for exoplanets, as I'll show in a second, you can actually disentangle those things very strongly.
Oh, but there's no significant difference within the giant planet and the rest, right? It's just a complete.
In terms of composition? In terms of composition, there is a difference.
Oh, I see.
Yes. Yeah, I'll show this in a second. Composition, there is actually quite a clear distinction between. Actually, I'll get to that right now. I'll just deal with that. Okay. So one question that you might ask, or has already been asked, is what is the composition of those planets? So Kepler gives us this axis, the radius of the planet. But in order to learn something about what they're actually made out of, you need another measurement, that is a mass measurement. So one of the most common plots to see in any sort of exoplanet conference is a planet radius versus mass diagram. And those are the only two things that we can really measure. We can measure the radius using transits, and then we do follow-up observation using the Doppler method to get the mass. And you can then place planets on this diagram, and you can draw lines of a given composition. So for example, you can say, okay, a pure rock will have this mass-radius relation, or a planet that is mostly rocky and has some thin hydrogen-helium atmosphere, say a given percentage, 1% or larger, will follow this line. Or if you just have a hypothetical pure water planet, it will follow this line. In reality, of course, there's degeneracies between these. For a given density measurement, which is really what you get, you can't really tell apart some of these solutions, for example, how much water there is and how much hydrogen helium there is. But one thing that we have learned is that there seems to be a turnover. So if you actually plot the density of the planet, so using the radius and the mass, versus the radius of the planet, you see that the density, and these are sort of filtered measurements, only using the best measurements that we have, that the density increases up to a certain radius. And then at that critical radius, which is about 1.5 Earth radii or so, the density starts to decrease again. And this has been interpreted as the signature of a transition between planets that are mostly rocky and those that have substantial atmospheres, including lighter elements such as hydrogen and helium. So here, as you build up, as you increase your radius, you essentially just compress more rocky material and you increase in density. And then at this peak and this transition radius, you essentially end up with planets that grow larger, but the densities become smaller because you just add up light elements in the envelope. So this is now sort of accepted, at least in the Kepler planet population, that there are two families, one that are mostly rocky and the other ones that are more gaseous, and that there's this transition radius between those two families. But one thing to keep in mind, and my caveat is blocked by the I guess I can't get rid of it anyway. So the caveat is that most, sorry. Yeah,
is there any correlation between heliocentric distance and type of planet? So, for example, the smaller rocky planets are also in its
That's actually exactly what this plot is showing. So this is now showing the density of the planet as a function of the same major axis, so how far away they are from their host star. And in general, there's no difference between the distance from the star and the size of the planet, which is sort of reflected in this plot. But there are some differences. So there are some certain gaps in the distribution of planets as they are when they're really close into the host star, because of effects that essentially strip the envelope of the planets. If you get a lot of irradiation, if the planet is very close into the star, the incident flux is very high, and there's some evaporation effects that essentially get rid of this thin hydrogen helium atmospheres that I talked about. So the caveat that I wanted to point out in this transition is that all of these planets are extremely close. I mean, this is now density versus the same major axis, and you see Mercury and Earth here. These are all the planets that I've shown you before. I think this is actually all the planets with density measurements. And you can see that all of them are, in fact, interior to the orbit of Mercury, right? So these sort of planets are very unlike anything that we know in the solar system. So whenever we say we've learned something about the composition, we have to be careful because these don't look like this, sort of far away from the star, where things are sort of nice and cool or just the right temperature. But they're very close in. They essentially receive a lot of incident flux from the stars. Okay, so I'll probably skip this and go to the habitable. So this is sort of leading into this question: can we actually detect planets that are similar to the Earth? Right. So I've just shown you that most of the Kepler planets are nothing like it because they're very close in and they undergo effects, for example, photoevaporation from the stars. So can we detect habitable zone planets? Well, the key question is where to look. And this is a classic plot from the seminal paper by Casting on the habitable zone itself. And that shows, so to define the habitable zone, it's sort of the normal way to define it, and there's lots of literature, in fact, what the habitable zone is. But in a hand-wavy way, you could say, okay, what's the distance from the host star where the incident flux of temperature would be right so that liquid water could exist on a planet. And you can define this habitable zone as a function of the mass, so the mass of the star, and the distance from the star. And this yellow area here shows you what the estimates of this habitable zone, would be. So a question for the students, the audience, why is it that the habitable zone is not, why is it a slanted line in this diagram? Why is it not just a vertical strip? Yes?
Because as the larger the star gets, the further out the habitable zone is going to be the star.
So what's the key factor there? What defines the habitable zone? What's the key quantity?
The mass of the star.
It's the luminosity which correlates with the mass of the star. So if you have an M dwarf, right? So an M-type star will be much smaller, less luminous, and so at a given orbital distance, at a smaller orbital distance, you will get an incident flux that's equivalent to the Earth. So this is why this is slanted, right? So at the sun, it's around about 1 AU, G-type star, but if you go to an M-type star, it's much closer in. So the first question is, can we actually find an Earth analog, something that's really like the Earth around a G-type star, and can we actually detect an Earth analog around it? And in fact, Kepler was made to answer that question. That was the key goal that Kepler was going to answer. And there is a candidate, there are candidates. This is Kepler 452b that was published a few years ago now. An Earth-sized planet around a solar-type star in an orbital period of 385 days, so perfect candidate. You see the transit light curve here, so this is the phase-folded transit. Remember that a little bit of light is blocked. And you can see that it's a pretty difficult measurement, right? You can see, oh, well, if you squint, you can sort of believe it if you look at the pin data points. Unfortunately, however, it's not quite as easy to make these measurements. Essentially, you only get 3 transits, right? Kepler observed for 4 years. This one has a little bit longer than a year period, so you only get a couple of transits. And in fact, just this year, there's been another paper that now claims that this planet actually doesn't exist, and it might actually just be an artifact in the Kepler data. In fact, it was even covered on APR. Earth's bigger older cousin maybe doesn't even exist. And it's a tricky situation because it's so small, it's so far away, we can't confirm it independently. We can't go and do Doppler measurements. As I mentioned at the beginning, we're not there yet at the precision to actually confirm these. So the jury is still out whether Kepler 452b really exists. We don't know, right? We don't know unless we actually develop technology to confirm it. So that means that it's really hard to find Earth analogs around solar-type stars. So what about M-type stars? This has been, in fact, one of the main focal points of the exoplanet community in the last few years. And that's because of the fact that we just discussed, everything moves further in. So you have a planet that's further in, so you get a lot more transits, can build up your signal, it's easier to do. The radial velocity signal is also larger. So there have been a few very high-profile discoveries over the last few years. Proxima b, the closest star to our sun, has a detected planet. This is the radial velocity signal, so this is detected using the Doppler shift. See the radial velocity signal here. Again, difficult measurements. You have to squint a little bit to actually believe it. There have been some follow-up measurements. I think this one is going to stick, so it's not going to be sort of removed again. And TRAPPIST-1, which is also an ultra-cool dwarf, which has, in fact, 7 transiting planets. So here you see the transits around them. And some of these, even though they're really close in, the star is so cool that the habitable zone is so close in as well, that they are in the habitable zone. The problem, however, is that cool stars are very active. So what happens with stars and stellar evolution, as we have in the sun, is that stars are active to give off high energy radiation. Periodically in the sun we have flares and CMEs. Stars do the same, other stars do the same thing, and in fact, cool stars do it even more so than G-type stars. So here's a light curve of Proxima b, and you can see all these spikes. All of these are flares that go off every few days, and that give off a lot of energy, a lot of higher energy radiation that then impacts the planet. The planet's really close, right, because the habitable zone is so close in. And we don't really know what that does to life. And there's a lot of literature that I won't have time to go into in detail that tries to answer this question: is it actually valuable to look for life around, cool planets that are very close in around cool stars? It's a very active field of research, theoretically, and also observation. Okay, so to wrap up, let me just briefly make a case for another place where we can look for life, and that is around stars that are actually around planets that are unlike the Earth. So here's a diagram that shows the planet radius. Just skip forward. The planet radius versus the incident flux on the planet. So this is now folding in the luminosity of the stars. And instead of using period, we're now actually folding that in, and we're calculating directly how much flux does the planet receive from the host star. So on the left-hand side here is high incident flux. So these are planets that are being baked by their star. On the right-hand side are low incident fluxes. And this is the Kepler planet population that Kepler has detected. And in green, I've highlighted here what we would mark as the habitable zone. So because we're plotting things as a function of incident flux, this is now actually a vertical band, not slanted line as a function of distance. So obviously the planets I have talked about are mostly down here, right? The small ones, Earth-sized. Those are the ones that we're interested in. But there's a whole bunch up here as well, Jupiters, that are in the habitable zone. So one of the questions, and in fact there was a recent paper that I found that explored this, is that you could think about planets around Jupiters that have moons, and those moons are in the habitable zone. Those moons could potentially also be places where life could develop. You don't have to necessarily always stick to the planet, but if you have a Jupiter around which you have a moon in the habitable zone, that might be another place with life. And they're actually not that rare. So we now know that about 5 to 10% of all stars have a Jupiter analog. So a Jupiter, I should say, a Jupiter in the habitable zone, not a Jupiter. So it's not a small fraction. But Jupiters are actually some of the least understood planets that we know of. As I've mentioned before, we actually have this huge population, although overall it's a small fraction of all planets, but we have this large population that's easy to find of hot Jupiters. And those were the first planets we found, but we still understand the least about them. We don't know how they came to where they are now. We don't know how they will evolve in the future. And it's still a puzzle as to where they actually come from. Why do we have hot Jupiters in our systems, but not in the sun, in the solar system? Okay, so with that, I think probably going to hand over to Ashley, because Ashley will actually be talking about a hot Jupiter system that we have investigated, that Kepler has observed, and from which we have actually learned something about these mysterious hot Jupiters. So just to emphasize, the hot Jupiters were found, the first type of planet that has been found, but we still haven't actually understand. We don't actually understand where they come from. So that's what it's
Okay. Thank you. So for those of you that weren't here, and actually I apologize in advance, today was a great day to lose my voice. So if you have any issues hearing me, just ask me to repeat. So I'm a third-year grad student at the Institute for Astronomy here at the University of Hawaii. Dan Huber is actually my advisor, and he just made my life a little bit more simple, discussing exoplanets, how we find them, and why the host star characterization is so important. So I'm going to take you through a journey through the past year and a half of my life on the confirmation and characterization of one special system, KOI4. So to start with a little bit of context, I'm going to start with the population of Kepler exoplanet hosts. This is both candidate and confirmed hosts, and I plotted this in log G, or the surface gravity of the star, as a function of effective temperature. And for all of the reasons Dan just explained, we really like finding planets around astroseismic hosts because these are some of the best characterized systems that we can find. So as a result, there were two main studies done on this. The first by Dan Huber in 2013. This is approximately halfway through the mission when half of the data was available. We found 77 seismic, he found 77 seismic hosts. And then there was a follow-up done by one of our collaborators, Mia Lundquist, and combining the two catalogs, we were able to find a total of 106 known seismic hosts. However, after these two studies were done, there was a re-release of data. And because my advisor was one of the first authors on one of the catalogs, figured it was a good idea for, as my first year research project, to basically go back through the data to do two things. One, to see if we can confirm oscillations in previously known hosts, and two, see if we could find some new seismic hosts. So what I'm showing you here are preliminary results of that study. Here, black represents the previously known hosts in which I was also able to find oscillations in with the new data. And then we have two new populations emerge here. We have this blue population down here. I say possibly non-oscillating. These are previously known hosts in which I was not able to find oscillations in the new data. We have not yet looked into if this was just an effect of the calibration or if this is in fact real. And then at the top here, we have a population of new seismic hosts. So I did find 14 new seismic hosts in this study. The rest of my talk is going to be focusing on one of these new seismic hosts, KOI4. So when the Kepler spacecraft first launched, the first three transiting planets were already known from ground-based observations. We have TRACE 2b, HAP-P7b, and HAP-P11b. And because these were known pre-launch, they were given the first three KOI numbers for Kepler object of interest. Very soon thereafter, the field of view was flooded with planet candidates. Just for reference, I'm going to throw KOI4 on the map there. And just to kind of really drive this home, because the first three were known pre-launch, KOI4 is therefore Kepler's first new planet detection. So first confirming the system, and more importantly, why was it not confirmed earlier? So the initial Kepler input catalog classified KY4 as a main sequence star. It was a little bit hotter than the sun, but approximately the same size. And as Dan just expressed earlier, what we're looking at here is a primary transit where the actual, the delta here is proportional to the ratio of the sizes of the planet and star. And because we have a planet size, a star size here, just a little bit, change my angle here. Because we have the size of the star, we can back out the planet radius. So around a main sequence star, KY4 was hosting a Neptune-sized planet on an orbital period of 3.85 days. And the catch here was that a secondary eclipse was observed. Now, Dan did not talk about this. So the primary transit is when the planet goes in front of its host star and blocks out starlight. But when the planet goes behind the star, we call this a secondary transit or eclipse. We're actually only losing light from the planet itself. And as Dan already suggested, the actual brightness ratio between the planet and star is usually on the order of parts per 100 million or billion. So in terms of Kepler detections, detecting a secondary eclipse of planets was actually quite rare. And especially for a Neptune-sized planet, this is just not possible. So as soon as the secondary eclipse was observed, KY4 was marked as a false positive. Now, my seismic analysis found that KY4 was not a main sequence star, but in fact an evolved subgiant. So it's roughly 3 times larger than the sun. So what I'm showing you here is the seismic detection for KY4. This is a power spectrum, so we have power density as a function of frequency in microhertz. For those of you that don't think in frequency space, I've put a more familiar time scale down here. And I know there's a lot going on, but what I really just want to show you is that where these oscillations are occurring right here, you can see this excess power. So solar-like oscillations, we're measuring these convection timescales. This is driven by near-surface convection. So this is a stochastic process, which is why you see this occurring over a range of frequencies. But in general, it's oscillating on the order of like 30 to 35 minutes. And as Dan said earlier, as you go down, so this is a bit more evolved, so it's happening on a slower time scale. And we know that the sun has the famous 5-minute oscillations. So this is about where we expect a subgiant host to be oscillating. So with this size star, this is consistent with a hot Jupiter. Now here, the secondary eclipse of the hot Jupiter planet that size would actually make sense, but that doesn't mean that the planet is brilliant. So we reached out to a collaborator who had already collected spectra on KY4 to see if they could take some more observations for us. And to our surprise, within a week, we had a beautiful RV curve, as I said before, it's a sinusoidal here, phased up with the period of the planet, therefore confirming the planet. The next trick was to characterize the system. Because we had both transit and RV data, we wanted to fit the data sets together to yield the most system parameters. Because there are some degeneracies that exist in this parameter space, so simultaneously fitting them together would give us the best results. So what I'm showing you here is basically a result, one final plot of the program that I wrote that fits transits and RVs together. So on the left here, you'll see something similar to what I showed earlier. We have the time from mid-transit of the primary on top, time from mid-transit of the secondary on the bottom here. The data is shown in gray, and then I've also bin data showed by those black squares you can see here. On the upper right-hand corner was kind of just a sanity check panel. This is the entire light curve, and I phase folded it to the period of the planet. So this is essentially just that blown out. This is like not turning over here. So this is the secondary eclipse, and this is the primary here. But what I'm essentially showing is that, so this is a 14-dimensional parameter space, and the light curve is over 330,000 data points. This is computationally very expensive trying to step through this parameter space. So essentially what I've done is just took 3 times the transit duration and essentially masked all of the other data. Because at least for purposes of this analysis, there wasn't any additional information we were gaining in these regimes. And then on the bottom right here, just basically showed just the plot I showed on the previous slide. This is the radial velocity measurements here. I've just overlaid the model. So what you're looking at here, so this yellow line shows the best fit model. I've also generated 100 random samples of the parameter space and plotted that with some transparency so you have an idea of the uncertainty in the model here. As Dan was saying earlier, we can measure planet inclination from the planet transit. And with that, I don't know if you remember that long equation he kind of showed at the beginning for the measuring the Doppler semi-amplitude, that actually helps break a degeneracy that exists and allows us to get a real measurement of the planet mass directly. I'm sorry, not directly, indirectly, but it's not a minimum mass measurement. So with that, we do measure a planet mass of 6 Jupiter masses, and then therefore confirm that KY4 is hosting a very massive hot Jupiter. So characterize the system, confirm the system, characterize the system. Why is this scientifically interesting? So if we go back to the diagram that I showed earlier, this time I'm only showing confirmed exoplanet hosts again, hosts in gray, and then hosts for which we have oscillations in black. And what I want to point out here is this, so this is the main sequence here. This is where the stars are in their core hydrogen burning phase. And as they exhaust all of their hydrogen and they start evolving, you can't really see it, but this is the red giant branch here. They go through this phase, this subgiant phase. As you can see, it's kind of a little bit sparse, and that's because this is a very rapid phase of stellar evolution. We don't know of many planet hosts in this regime. And not only that, actually something I wanted to point out, if you take a look at the measurements here, these are pretty large error bars. And this is a result of this rapid rotation that the star is doing. And with rapid rotation, it makes these measurements really difficult to do because it's broadening these spectral lines. And because it's rapidly rotating and it's a bit more massive, we believe that KY4 evolved from a little bit further up in the main sequence and didn't have a convective envelope to effectively spin the star down through magnetic braking. And this is, of course, interesting because I have detected solar-like oscillations which demand near-surface convection. So at some point in its evolution, it's acquired this convective envelope, which of course has implications to the planets that orbit it as well. If we take a look at it in another parameter space, here I plotted all short-period planets, short period meaning anything with an orbital period less than or equal to 100 days. I've plotted it in a semi-major axis for the orbital distance as a function of stellar radius. We have planets, as you already said, a majority of our planets are found by the transit technique, which I've shown by the circle, and any of the other planets that are detected by any of the other various methods I've shown by triangle. And then I've colored in short period planets around evolved stars. And here by evolved, we mean anything with a stellar radius of 3 solar radii or larger. And you can already see by eye that this is not a very large population of planets, and that's correct. This is the most up-to-date version of this plot. I just made this. So there are only 18 evolved hosts known to host short period planets. And not only that, but KY4 is now the closest known planet around an evolved star. So this has really become a hot topic in the exoplanet community. Essentially, where are these planets, or what is happening to these planets as they're orbiting stars as they evolve off the main sequence? So one current theory is tidal evolution. We know that tides are governed by gravitational interactions in a system. And if we think about the one that we know best, the Sun-Earth-Moon system, we know that the tides in our ocean are very sensitive to basically the orientation of the Sun and the Moon with respect to the Earth. And I've included just kind of like a cartoon diagram here, obviously drawn not to scale. But on the left here, you can see that the Sun and Moon, both their gravitational forces are working in the same direction. So you have large differentials between the high and low tides there, corresponding to the spring tide. However, on the right here, you can see that the Sun and Moon are perpendicular to one another. So they're working almost perfectly against one another. And as a result, you have less of a differential here between the high and low tides. So I'm going to define a tidal equilibrium state as a coplanar circular synchronous orbit. What does that mean? Coplanar just is the orbital period of orbital plane of the planet or planets aligned with the rotation axis of the star. If we think of the solar system, we know this is mostly true with just some small angle. And also similarly, most of the planets in the solar system are on mostly circular orbits. And now for synchronous rotation, just want to think about the Moon-Earth system, and that the Moon has a rotation period that is equal to the orbital period. And it's rotating the same way that it's orbiting, and that we only ever see one side of the Moon. And this tidal locking feature has an effect on the Earth, right? It's slowing down the rotation of the Earth because it's working to sync to the rotation of the Earth with the orbit of the Moon on timescales, which are obviously not measurable, but it is happening. And so the orbital period of the Moon is much larger than that, the rotation period of the Earth. And there are special cases in which this is not the case. It's kind of already surpassed this critical point and is not able to reach an equilibrium state. And this is the case with KY4. So KY4, we know that the planet is on an orbital period of 3.85 days. We're actually lucky enough to get signatures of stellar rotation in the light curve. And we measure that the star is rotating at a period of 5.5 days. So the opposite is true here. And when this happens, the planet is transferring angular momentum to the star, which causes the star to spin up. And the only way that the system can compensate for this is basically by shrinking. It's a shrink in orbit. And because it's already surpassed this equilibrium state, this planet will migrate in until it's eventually engulfed by the host star. So this is more commonly referred to as orbital period decay. So it turns out that we can measure this time scale of orbital period decay or tidal dissipation by this equation here. We have the quantity A, the semi-major axis or orbital distance over the stellar radius to the fifth power. It's highly dependent on these two parameters. Excuse me. And then we have the mass ratio of the star and the planet. And I want to draw your attention to this parameter here, the Q star prime. This is commonly referred to as the tidal quality factor. So the reason the time scales are so uncertain is that is for this tidal quality factor. It's a single parameterization of all the physical processes that happen in tidal dissipation. And it's essentially, and I know I use a subscript star here, but this is true for any celestial body. It's basically how susceptible is this body to these tidal effects. As a result of a single parameterization, this tidal quality factor is not very well understood. In fact, literature values span several orders of magnitude, where the current accepted value for a main sequence star is about 10 to the 6. But because we expect this timescale to be quicker and more evolved stars, we expect it to be closer to the 10 to the 2, 10 to the 3. But because KY4 is on such a short orbital period, we have 4 years worth of data, we can try to model this pretty well. We have a lot of transits, so this is one of the benchmark systems to test this analysis. So we can model this by going from a linear ephemeris, or constant orbital period, to a quadratic, just by adding this second order term here, where delta P is corresponds to the decay rate times the period. Or this can just be thought of as the change in period for consecutive orbits. All right, so let's take a look and see if we can detect orbital period decay in KY4. So we start out with 262 transits, for which I've measured the individual times independently. And I have this plotted in what we call an O minus C, or observed minus expected, in minutes as a function of the transit epic time in days. And this can really just be thought of as the deviation from a constant orbital period there. So I'm just going to bit over half years and then just kind of zoom in, because it doesn't happen that fast, or at least we don't think it does. So I've added some literature values up here at the top, and I've also added a 0 point there. This is again just equivalent to assuming a constant orbital period. So when we model this, we do get a negative value for delta P, which is indicative of period decay. This corresponds to a decay rate of about 40 milliseconds per year. However, you take a look over here, this is 1, 2, and 3 sigma. Within 1 sigma, the answer is consistent with 0. So while we don't detect orbital period decay over the Kepler baseline over the 4 years, what we can do is put an upper limit to how fast this process can happen. And then by plugging it back into that equation I showed earlier, we can actually put a lower limit constraint on this tidal quality factor in more evolved stars. So to 3 sigma, sorry. So 3 sigma, the decay rate is about 0.4 milliseconds per year. And that corresponds to a tidal quality factor of about 10 to the 4. I've added some other literature values here so you can see that the analysis clearly rules out. And I just want to take a moment to emphasize the importance of this, because this is the first time observationally we've ever been able to put any sort of constraint on this tidal quality factor in more evolved stars. And I also want to just draw your focus over here. We've effectively ruled out 2 orders of magnitude for this tidal quality factor. And KOI4 is bright enough with deep enough transits that it can be observed from the ground, so you can extend that baseline and potentially get a better handle on this period decay and thus the tidal quality factor in more evolved stars. So with that, because I want to leave time for questions, I'll just leave my conclusions up there, and Dan and I will take any questions.
And for people in Zoom land, I've got the chat room open, so if you have questions, we'll look at them. But, well, I had an interesting question from Dan's part of it. We were talking about the Jupiters and habitable zones. The Jupiters themselves wouldn't be habitable, so maybe the exoplanets could be. But in our own solar system, that's a really harsh radiation environment. We worry about spacecraft living very long. Would you really consider a moon to be habitable?
A radiation environment?
Because the intense magnetic field of Jupiter having ions.
Sure. Yeah, to be honest, that's not something I know too much about. I know there's definitely literature where they have, I mean, I guess it depends on what the properties of the moon are. Way, perhaps there's some way where you can skip that depending on the atmosphere. Perhaps you can get an atmosphere where you can skip that. But yeah, it's a good question. It's definitely not the usual place where you would think that you would find a habitable planet. That's why there was always this focus on finding an Earth animal, because that's what we know it works, right? But yes, it's a good question. The influence of the radiation from the giant planet itself. Sure, it's been considered in some ways.
You can always go underground.
Right, yeah, of course, yeah. Exactly. I mean, it's also the fact that we haven't actually found any moons yet. So there's no detection of an exomoon. People have tried really hard, but it hasn't succeeded, which is a bit surprising because we think, well, planets are everywhere, it should be that too. But it's a difficult measurement to make. It's essentially a distortion on your transit shape, right? Think about it, a planet going in, then you have something on the side, you get a asymmetric transit essentially.
So I have a question that goes beyond this. So we now have some habitable planets. How do you make the leap from habitable atmospheres, or where does this go?
Yes, that's the goal. I mean, I actually had a bit of some slides in the future of what's coming next, sort of the NASA roadmap, right? So NASA likes roadmaps, and putting things on, what's the next mission? And the next mission after, so this one, the New Worlds that may happen in our lifetime is essentially after JWST and W first, an mission to directly image an Earth animal. And the way to go from is it habitable to inhabited is to look at the atmosphere and look for what they call biomarkers. So any kind of signature of ozone or anything that you might think is not naturally produced by an environment that has to come from something that life, intelligent life, perhaps. There's of course other ways to do it. People look for radio signals, so this search for radio signals with SETI, but it's still going on, in fact. So it's another way to do it. But that is on the NASA roadmap, the next thing. So the sort of roadmap is the TESS, which is right now in fact launched, and that we're going to be working on is finding planets close to us that we can then characterize the atmospheres of, and then the next generation will go out and hopefully find real. So that's the only way to do it.
Just follow up on this question. What are the biomarkers?
Good question. They're probably better people in the audience to answer the question than astrophysicists, but I don't know. I mean, I guess.
Chlorophyll in the atmosphere.
Yeah. Vegetation, anything that you might associate with plants or.
Chiral molecule.
I mean, that all depends on how easy it is to detect in a spectrum at a given resolution. These are going to be very hard measurements to do.
The question follow-up is, what's the shortest distance for the exoplanet? So is there any way to make an instrument that can do a direct measurement?
And closest to the Earth?
Light years away. So most of the measurements will be just past measurements.
So you mean closest to us, to the Earth, or to the
so
star?
from our solar system, then we are not finding anything. And so the next solar system, probably what is the shortest distance so far?
So I've shown it actually. Proxima b is the closest star to our solar system. It's about 4 light years away. And we have found a planet that we believe is in the habitable zone around that star. And there are ideas, you have heard about the Breakthrough Initiative from Yuri Milner, who's a billionaire living in Silicon Valley, to send small spacecrafts towards Proxima and actually to image it, an imaging sort of type mission to pick them. But it's still very far away. I mean, we found a planet in the habitable zone around the closest star. So we could, I mean, it is basically, you can't get any more lucky than that, I guess. The problem is that we don't know its size. We only know its mass. In fact, we only know its minimum mass. It's a Doppler detection. I showed it in the slides. So Proxima b has I think it's 1.2 Earth mass, minimum mass planet in the habitable zone. It's not transiting. We'll have tried and looked. Unfortunately, it's not transiting, so the geometry is just off. But that's a system that you can be certain will be studied a lot more. And but Proxima b is also very cool anymore. So same problem that I've said before about habitability and stellar activity affects Proxima b. But that's as close as you can get. But TESS will find, the whole goal of TESS, which is to follow Kepler, is to find the closest planets to our solar system. It looks at very bright stars. In fact, just today, NASA released the first light image from TESS. So TESS has 4 cameras. It's a very large field of view instrument. It's 4 cameras, and it looks essentially from the ecliptic plane all the way out to the ecliptic pole. So those are the 4 cameras. And it looks for transiting planets around the brightest stars. Because it is such a large field of view, it only, there's a lot of confusion because the pixels are quite large. So it's focused on the largest planets. So what you see here are the Magic Mountain clouds. So it started in the south. That was just released today. I guess that's a much larger cloud. So actually, in fact, for our dissertation, we'll work with TESS data to characterize the planets that TESS has found in various different. So we're pretty excited about the first light image.
So Ashley, how long will KOI4 spiral into its star? Do you have enough information for that yet?
Well, because our detection, because it's consistent with 0, we can't make an estimate on that time scale. But what I was saying is we can't, because it is bright enough with deep enough transits with a 0.13% transit signal, we can measure from the ground, and even getting a measurement now will extend that baseline to 10 years, and hopefully we can get a better, more confident handle on the orbital period decay and thus the tidal quality factor, and then we can get a better estimate on the time.
Planet to the star is only 3 times the size of the star, so not very far. But there's only a single planet where orbital period decay has been detected so far. And this is the second best candidate.
Right, and that was around a main sequence star, so this is the first detection around an evolved star.
But it was also longer time set.
Yeah, they actually did something similar, but were able to use some Parkes data to get a signal out of that, and it also extended it to about 10 years.
Yeah.
questions from our Zoom lab? We actually have quite a crowd on. There's like 8 people. No questions from Zoom? Any more from our audience here? Well, if not, let's thank Dan again. Again, a reminder.